All right, that's cool. All right, hi everyone. Welcome to week 15. Um, Today we'll be covering some geo problems, and we'll probably also be doing some walkthroughs of some final fives. So basically, what we call the final fives are basically the last five problems of the MC8 contest. And so we just wanted again, like we want to give you guys more problem solving practice because AMC8 the AMC8 contest window is about a week, so around like 6 days, and because of that, you guys should definitely get as much practice as you guys can, um, as close to the actual contest date. To so like whenever you're taking it. So yeah, let's just get started. Let's just by finishing up. Um, we only have three problems left for geometry that we didn't get to finish last time, so we'll be doing that. And well, I guess we'll see what we're going to do with the other 30 minutes, and so we'll be playing that out right now. Okay, so I'm going to read this problem, and you guys should definitely think about it before I walk through it, of course. So 2024 MCA problem 3. We're starting with a problem on the easier side, and it reads four squares with side lengths 4, 7, 9, and 10 are arranged in increasing size order so that their left edges and their and bottom edges align. The squares alternate in color white, gray, respectively, as shown in the figure. What is the area of the visible gray region in square units? All right. So just pause, take a and just think about it. Think about it. Okay. Yeah, we'll be walking through it. Well, that's good that you have a preliminary answer, and it will be good if you guys can drop in the chat how you guys did it, so that we can learn from each other's different approaches, because there's always more than one way to approach a problem, and especially for easier problems, it's really good to know that there's not uh, one single way to do a problem, because the more ways you know how to do a problem, the more versatile problem solving tools are for harder problems. All right. So if anyone has an idea, you guys can drop that in the chat. So I'll give you guys like 1 minute more to just think about this one. All right. To start off, um, how are we gonna think about this problem? Well, first, let's think about what we're actually trying to find. Um, yeah, I just saw these messages. Yes. Uh-huh. Yes, that's probably the easiest way to do it. Yeah. Um, and both of you are correct. And so I'm just gonna walk through it just for uh, I guess just to do it one more time. So because we want to find area of the visible gray region in square units, we can actually uh, we can actually use a very nice strategy uh, that you can actually use for harder problems, which is by subtracting the area of a big area. So that's if you have this red area, let's call it A, and if you have a smaller pink area called B, then you can actually find the surrounding the green area. So that is in A but not in B by subtracting the area of B from the area of A. And so we can say that the green region is the area of A minus the area of B. So we can use that concept to find the area of the gray region. So what can we say about this gray region right over here? Well, we can say that this big square, so the square of length 7 minus the square of the area of the square of length 7 minus the area of the square of length 4 will equal the gray region. So if we want to denote that with colors to make it even more clear, we can say that the whole area, I'm just going to outline this in red, the whole area in red right over here minus the whole area in pink right over here. Basically, it represents our areas A, A and B, like that. If we subtract B from A, then we're going to get the green area right over here. And so since the area of a square, if you guys don't know this formula yet, area of the square is just s squared for a side length s. The area of the square is s squared. Then we can say that this first gray area is 7 squared, which is the big area, minus 4 squared. And then we can use a similar reasoning for the outer gray area right over here. And so the big area this time is the square of side length 10. So that's just 10 squared. And then we're going to subtract the square of side length 9, and then you're going to write minus 9 squared. And so after computing that, you should get, well, let's just do it real quick. 49 minus 16 plus 100 minus 81. I'm just going to combine the positive terms. Get 149 minus 97. That is 52, as many of you guys have said in the chat. So nice job for everyone who got it. Obviously, as I said before, there are many ways to approach this, but this is probably the simplest way, just because you are given the side length of the squares, and the gray areas are really easy to represent in terms of the areas of the squares. So namely, there's just a difference between the area of a big square and the area of a small square. So if you like to think about area conceptually, which I do, because it's kind of like uh, it's kind of like having a cookie and then cutting out like a gingerbread man from it. And so what you're left is basically the cookie mold uh, without like the shape of the gingerbread man. So that's what I like to think about it with this area concept right over here. And so reason why this is like the simplest way to do it is that the gray area is kind of like that. You can think about it as a big square, and then so if you shade in the whole big square and then take out little small square, you're going to get, so you're going to take out this part. What remains is just like a painted rectangular region. Yeah, that's how. Again, area is best to think about it intuitively and not in terms of like formulas. So, because formulas uh, uh, are like a part of like the computation. Like obviously, you need to know that the area of a square is as squared, right? But how you actually get the area in this specific problem needs a little bit more creativity. Um, and then so the another way to do it is obviously just split it up like that. You could like split the region in many ways, but I find that splitting it up is a little bit more work, simply because you got to find like the side lengths of this, the side length of this, and the side length of that, and then it's kind of like you just have to do more work to get the actual area. Whereas like subtracting the part from the whole will give you the gray areas very easily. All right, cool. All right, so uh, this is another error problem. Error problems are going to be really frequent on the AMC 8. And so let me just give you some, because I don't think we have covered the area formulas that much, but I think it's very important to go over them real quick. So the basic area formulas, the basic area formulas that you need to know for the AIMC 8 are the following. So with the square, if you have a square, obviously the square is a rectangle with all equal lengths, side length s. Then the area, so the area, I'm just going to denote it as capital A. It's going to be s squared. And then for a rectangle, it's going to be if you have the length as L and the width as W, the area is LW. That's for a rectangle. If you have a circle with radius R, the area is going to be pi r squared. And this is a little bit more like these two are like really are a little bit easier to prove. This one is not as easy to prove. Um, the the one way that I can think of at the top of my head to do this is through calculus. But obviously you need to know that for MCA. But just like for the simple area formulas, such as that for the square and rectangle, you can obviously search up the proofs, and I encourage you guys to look into them more on your own time. So circle is pi r squared for a radius r. Excuse me. If you have a triangle with a base b, height h, then the area is going to be a half bh. Obviously, you've seen some of these in school, but these are basically the well, these are the basic formulas that you really need to know for the MCA, and a lot of the other ones can be rederived from these four. And so let's just look at how we can apply that here. So the figure below shows a large white circle with a number of smaller white and shaded circles in its interior. What fraction of the interior of the large white circle is shaded? Okay, that's interesting. So this, I think one of the best ways to improve math intuition is to think about the connections. I don't think I realized this until later in my math competition journey, but what I want you guys to see, especially by after doing this problem that we did first, is that there's shaded and unshaded regions in this diagram. And if you look back at this problem, there are also shaded and unshaded regions. And so seeing like these two similar properties across these two problems, you might be wondering like if we could like, is there, obviously there are two different problems, but is there a way to connect them in such a way that like knowing how to solve one problem and the main ideas um, of how to obviously how to do the problem, one problem can that lead me to have a sense of what to do in the other if I don't know how to do the other problem. So that's basically one of the most powerful senses that you can have like during a contest. You it's when you're stuck, like you don't know what to do. You've tried it out, you've tried a problem, um, and it's probably looks like really daunting, but you have that sense that you've seen a problem in the past that it seems familiar, seems somewhat familiar. Like it doesn't, it's not obviously like the statements are not the same, the problems are different, numbers are like are nowhere near each other, but like no, but like in this, let's say you're stuck on doing this, but you've done this, you can think, well, we had shaded regions here, and we did something like this, something where we had a larger area and subtracting a smaller area from the larger area to get the shaded region. So what if we can do something similar with this problem? It turns out we can. And so I'm just going to walk through this problem just to show you how we can kind of apply the concepts that we did here, that we had here in 2024 MC8 problem 3, and uh, and basically use it here. And so this also kind of explains why doing past problems is really effective. It's because the uh, MA doesn't generally give like a completely brand new test where like all of the problems are have concepts that like you've never seen before in like a past practice exam you've done. Like that doesn't usually happen. They usually have like a like they usually have a subset of concepts that they actually pull up. So you're not going to see like something brand new like calculus that like you're going to need to use on an MC8 problem, right? But in this instance, we can use area, and so let's do that right now. So, so what fraction? Again, let's look at what we actually need to find. What fraction of the interior of the large white circle is shaded? And so, what's the large white circle? Well, it's gonna be just a big circle, the biggest circle you see. And so, let us denote uh, because we're given grid lines which you don't usually pop up that often. Um, and yes, yes, and that's how you approach it. Yeah, you gotta want to use the concept of subtracting the small area from the large area. And so let's just denote the one unit, one grid unit as one, just to make everything easier. And so um, because we want to find what's a fraction of the interior of the large white circle, let's just find the area of the large white circle. So again, we denote area using brackets, and so we can write large white circle like that, and that's basically denotes the area of the large white circle. And so the area of the large white circle, well, what is that? The radius is going to be 3, as drawn right here, just 1, 2, 3, like that. And so the area is going to be 3 squared pi, pi r squared. I just wrote it like that. Um, it doesn't really matter how you write it, just as long as it's pi r squared. So the area is 9 pi, and so we want to find the shaded region. And so the shaded region, uh, obviously, uh, we can split this up into many different parts. And so if we want to find the area of the shaded region, we can first find the area of the 3 small circles. And so the 3 small circles have radius a half because their diameter is exactly one grid length. And so one grid, since a grid length is one, half of that grid length is half of the diameter, which is a radius, which is a half. So we have three circles of radius a half, like that. And so for this funky shaded region, we can just subtract the area of this circle minus the area of this circle. So we're going to subtract the area of the big. So the area of the big is going to have 2. So if you consider this, this has to be the center of the big circle. And so this radius is 2. And then the area is going to be 2 squared pi. And then we're going to subtract the area of the smaller circles. And that's going to be 2, because we have 2 circles, times 1, because the radius of these green circles is 1. And so that's going to be 1 squared pi. And so computing that, we're going to have 3 times a quarter squared. A quarter squared is a quarter, a half squared is a quarter. And so that's going to be 3/4 pi. Plus, this thing is 4 pi. This thing is 2 pi. So 4 pi minus 2 pi is 2 pi. And so this thing is going to be 11 over 4 pi. And so now we can just find our answer. The area shaded, the area shaded over the total is 11 over 4 pi over 9 pi, which is 11 over 36. And that's B. And yes, right. Yes. Yes, you can take the pi out. Yeah, yeah. Uh-huh. Yes. Yes, Hubert, you're correct. And uh, May brought a really good point, is that you can obviously take the pi out. I think yeah, yeah. Like in this final computation, you do have to take the pi out, because like obviously the top and bottom have the pi, you can just cancel that out. But in the actual computation, I would say, like, even if you know that the pi's cancel out, you would probably still need to leave it, leave the pi in the computation, because simply because the area of the circle is pi r squared. And so if r is like an integer, then you're gonna obviously have something in terms of pi, and I think it's best to leave the pi there in your computations. But when you're doing the actual ratio, we can do you can just cancel the pi. All right, cool. All right, so we have all right. I'll try to do this problem in time. But if I won't finish, Sid will carry on with this. So let's just read it real quick. Rectangles R1 and R2 and squares S1, S2, and S3 are shown below, combined to form a rectangle that is 3322 units wide and 2020 units high. What is the side length of S2 in units? All right. Okay, cool. So I think I pulled this up from a more I think this is definitely a Final Five, and I think this is a really good example to show you guys, because this is a hard problem, and I think we can definitely leverage some of our problem solving skills. So I'm just gonna walk you guys through how I'm gonna like think about this problem, and I guess we'll see where we go from here. So, so one thing that's interesting is that we have squares, and so when I think of squares, I think of equal side lengths because a square obviously has side lengths, x x x, like all the side lengths are equal, and that's something really nice about squares that we can possibly exploit. Um, and so we have two rectangles and three squares, and they combine to form a rectangle that is 3 3 I have 3322 units wide, and so the width is this, the length is this. And so if you have trouble, if you confuse like length and width with each other, you can think about like length uh as like a like if you can just imagine like a ruler in the air, because like if you're measuring length, you usually like stick it like horizontally instead of like vertically, unless you're oriented sideways, but usually like you don't usually measure sideways, so you usually measure from left to right. And so length will be from left to right, and that's well, okay. Well, in this example, the width is actually the length. Well, what it says is wide, and that's because if something says it's high, so if something says it's like 2020 units high, then we got to put 2020 on the vertical axis, and so 3322 will be actually the length. My bad. Um, so that's what we're given, and we're given. And what is the side length of S2 in units? Okay, so again, what I that's something like the main thing that stuck out to me right here was the squares. Squares are really really nice. There's so many properties about squares. You guys should definitely look them up. Again, if you have time. But again, squares, like I just think of equal side lengths. So let's just assign variables to the side lengths of S1, S2, and S3, and let's just see what happens. Because I have a feeling that something good will was at least like we can make some equations from these variables, because 3322 and 2020, there's probably nothing special about them because they're the length and the width. But again, we want to say that S2, what's the side length of S2? And so if that's one of our variables, we can solve for that variable. And so let the side length, let's take this. Let side length, let's the side length of S1 be A, S2 be lat of S2 be B, and lat of S3 be C. So let's just label them real quick. This will be A, this will be A, this will be A. And before we label that A, we're gonna say that we're gonna actually label S2 first, and you see why. So this small segment right over here will be B, this will be B, this will be B, this will be B, and then we're gonna label S3 as C, except for one side length. And so what can we say about this side length? Well, because this side length is B, we can say that this side length highlighted is A minus B. Because if this side length is B and this side length is A, we can subtract, again, we can subtract the part from the whole. That's a really important concept in geometry. And so uh, so this thing is going to be A minus B, because this is a rectangle. So this side length is going to be A minus B because it's a rectangle. And so I'm just going to zoom in real quick. By the same logic, this is C minus B. This is C minus B. And so this side length is going to be A plus B. This is going to be B plus C, because we're adding the side lengths of S2 and S3 together, and that's going to be the side length of R2. So that's going to be the length of R2. And so we can write, and we something really nice that happens is that we can write A plus B plus C is 3 3 2 2, and um, a minus a minus b plus c is 2020. And look what we got. If this doesn't strike out to you already, we can see that the whole thing's almost symmetrical, except that there's a plus b in one equation and a minus b in one other equation. And so remember what we were trying to ask, what we are asked to find. What is the side length of S2? Well, that's why the squares idea, of like assigning variables to the squares, like stood out to me the most, because we're asked to find the side length of S2. And so if we had variables, um, if we assign the variables to the side lengths of all the squares, then possibly we can use this information. uh, yeah, it should be. Yeah, I think so. Yeah, we can use this information to solve for B. And so look, we don't even actually have to solve for A or C, because we want to find this boxed length, which is B. And so how do we get B? We can subtract the second from the first equation. And so the A's will cancel out, then we'll get 2B equals 3322. 3322 minus 2020. That's going to give us 11302. Yeah. And then B is 651, as someone mentioned in the chat. And that's correct. Cool. All right. So just to, yeah, oops, it is moved a little bit. So just to recap this problem, again, like squares, there are a lot of properties about squares, but like one key strategy, that you shouldn't have to memorize, that we should use squares, but one key strategy is letting side lengths be variables. So that's one key strategy that we used, and that enabled us to solve the problem effectively for what we want to find. In this case, S2 equals B, and we basically formed equations out of the side lengths that we eventually wrote in terms of the side lengths of the squares. And so we formed equations and we solved for B, and that got us our answer. Cool. All right. Thank you guys. And Sid will be moving on with more MC problems. Woohoo!
All right. Hi guys. Thank you, Daniel, for the lesson, and I'll be covering some final fives from the MTA, and these are final fives. Sorry. So these are final fives taken from the most recent AMCA, which was last year. Just to give you guys a feel of what can show up as difficult or later types of problems that are usually assumed as being difficult in the MCA. And so, as we walk through these problems, some problems are hard, but usually there's usually some in the final five, usually one or two, that are actually pretty approachable. It's just that since they're given the title of being final five, usually everyone assumes that they're hard, but sometimes that's not the case, as we saw with this problem right here. And uh, yeah, so as we saw with this problem right here, that's not always the case. And usually, like if you saw that this was a square and you and like exploited that symmetry, then this problem worked out well. And yeah, so even though final fives, some of the final fives can be hard, they're usually pretty approachable, like some of them. So let's start with this final five. It's not a geo problem, but it's still a final five. So um, we'll be covering this. We'll be talking about this problem now, It says a group of frogs called an army is living in a tree, right? A frog turns green when in the shade and turns yellow when in the sun. And so initially the ratio of green to yellow frogs was 3 to 1. And then three green frogs moved to the sunny side and five yellow frogs moved to the shady side. And so now the ratio is 4 to 1. And so what's the difference between the number of green frogs and the number of yellow frogs right now? Right. All right. So when I look at this type of problem, I usually want to uh, look at using the information that's given in the problem and turning it into variables or equations that I can solve, right? So first of all, let's read what this problem says. A group of frogs is living in a tree. Okay, a frog turns green when in the shade and turns yellow when in the sun. All right. So what can I do here? Maybe I'll say number of frogs that are in the shade. Maybe this is G, and then number of frogs in the sun is yellow. Notice that I didn't use shade and sun because they both start with S, but you could have defined it either way you want. But just to make it more easier for myself to remember and for you guys as well, you guys should always label your variables with the most I guess with information that's given in the problem, and also variables that like are going to help you remember what the variables actually stand for. So here a frog turns green when in the shade, so I label my variable G because it's easy to remember, right? And similarly for yellow as well. And so what happens is initially the ratio of green to yellow frogs was 3 to 1. And so this is all initial, by the way. I haven't really talked about the final condition yet. So now it says initially the ratio of green to yellow frogs was 3 to 1. I can establish a relationship between G and Y now, right? So I can say G over Y equals 3 over 1, right? Because uh, it says that the ratio is uh, 3 to 1, right? And then what happens is the three green frogs move to the sunny side. So what does that mean? So so we had G in the beginning, and then three frogs from this number of frogs, which was G, moved to the sunny side and became yellow, right? Because it says uh, when you go to the sun, you become yellow, right? So we lost three frogs, and yellow gained three frogs, right? Because basically we have G frogs in the beginning and yellow has Y frogs in the beginning. But three of our frogs went to yellow. So what happens is three of the green frogs moved to the sunny side. So so we lost three frogs, but the yellow green gained three frogs. And then but then it also says and five yellow frogs moved to the shady side. So what does that mean? That means that five of these yellow frogs. So we have y plus 3 now and g minus 3 now. But what happens later is that five of these yellow frogs, so we lose five yellow frogs, so minus 5, because they go to the sun, because they move to the shady side. And so if you go to the shady side, you become green. That's what the problem says, right? So uh, if you're moving to the shady side, you're turning from yellow to green, so you lose five yellow frogs, but you also gain five green frogs because when you move from the shade to the sun, or from the sun to the shade, you become green, and so the green populations gaining more frogs as colors, right? So now the last part of the last bit of the problem says that the ratio is 4 to 1. This means g plus 2 over y minus 2, because g minus 3 plus 5, we add these up, right? And we get whatever the ratio, and then we get what. So to establish another relationship, we say that the ratio is 4 to 1. You're right. So now what can we do? Well, we have this equation. So when I see a system of equations, usually one of these two strategies come into my mind, which is either elimination or substitution. Uh, Actually, let me simplify this first of all. So it says g equals 3y. Well, is eliminate? Well, can I use elimination here? Um, Yes, but I would, but as you'll see, it's better to use substitution because you already have that a variable is equal to 3y. So you can just substitute g equals 3y for g here and then solve for y. Does that make sense? So you just have a y and then you can easily find g and then work out that final answer, right? So plugging that into this equation, we get 3y plus 2 over y minus 2 equals 4. Okay, I'm just omitting the 1 because 4 over 1 is just 4. So 3y plus 2 equals 4y minus 8. And so uh, we see by rearranging this equation y equals 10. And so if y equals 10, what's g? Well, g is 3y, so g is 30, right? But here's where some of you may go wrong. You'll say, um, so you have to read the problem statement really carefully. It says, what is the difference between the number of green frogs and the number of yellow frogs now? So now is after all these transitions come through, right? So initially 30 minus 10 30 minus 10 is just 20, right? So you guys can go ahead and put D, right? And you're done. But no, it says what is the difference between the number of green frogs and the number of yellow frogs now? So now means that you have y plus 2 yellow and or y minus 2 yellow. My bad. I'll just so y minus 2 yellow and g plus 2 green, right? So these are what you have now. So if you have g in the beginning, you have g plus 2, so 32 now, right? And if you have 10 in the beginning, you have 10 minus 2, which is 8 now, because you just substitute that there, right? So you have 32, and now you have 8. So when it asks you for the difference between g and y, or the number of green frogs and yellow frogs now, you just say, oh, you have 32 minus 8, which is 24. So it's really important to read the problem, because if you don't read the problem, then you can make the silly mistake of just saying 20 and moving on instead of reading this one little word, now. And so now means that you have to account for all the transitions as well. So yeah, I guess this is a very common pitfall, especially in these competitions, because test writers write the problems pretty cleverly, I guess, accounting for different mistakes that like test takers might make. So just make sure you don't fall into that trap. But overall, I think this was a very approachable problem if you knew things about ratios and solving simple systems of equations and algebra. So definitely don't get scared when my basic point is, don't get scared when you see final fives in the MCA, because oftentimes they might not be as hard as you think they are. All right. So now we'll do this problem. Actually, before we do this problem, I'd like to cover this problem. So this problem says John has made a piece of stained glass art in the shape of two mountains, as shown in the figure below. One mountain peak is 8 feet high, while the other is 12 feet high. And the peak form a 90-degree angle, and the straight sides form a 45-degree angle with the ground, so like 45 and 45. Right? And so the artwork has an area of 183 square feet, and so The sides of the mountain meet at the intersection point near the center of the artwork, 8 feet, 8 feet, each feet above the ground. I can't speak. And so, what is the value of each? Right. So, first, let's try to understand what the problem is saying. So, we have two mountain peaks, like as you see mountains in the picture. It's just like that, and one is 8 feet tall, and one is 12 feet tall, right? And the straight sides form a 45-degree angle with the ground, and the total artwork. So this total area has an area of 183 square feet. And so the sides of the mountain meet an intersection point. So like right here, near the center of the artwork, with which is each feet above the ground. And so what is the value of h? Right. So in solving this problem, we can um, we can think of a couple of different things, but there is usually you can usually solve. Yeah, you can. There might be a way to solve this, like with a lot of computation and stuff. But usually in geometry problems, once you um, see triangles or something, okay. First of all, do I know how to find the shape of this figure or find the area of this shape? No, right? Because or at least I don't. So I don't know how to find the area of this shape. But maybe, but since these look like triangles to me, right? This looks like triangles to you guys, right? So if this shape looks like triangles to me, or two triangles, almost two triangles, um, I can find the area of those, right? So why don't I try to construct triangles in this example, or in this problem, such that we can uh, we can calculate the area and get to the answer more efficiently, right? So how about as I was saying before, this is almost two triangles, right? And so maybe uh, we can fill in the almost part. So like something like that. Uh, Let me draw this more clearly, right? So something like that, and maybe something like that. Yep, that seems like two triangles to me, right? Because this is H, so this is a triangle, and this is a triangle, right? But as we'll see, this makes the problem a much easier problem to handle and approach. Why? Because look at this, right? So if we tackle on this triangle, I'm gonna do it in blue. If we focus on if we focus on this triangle in the beginning, right? What do we know about this triangle? Well, we know. So we're focusing on the big triangle first. So what do we know about this triangle? Well, we know that this is 45 degrees and this is 90 degrees. And we need to find this angle, theta. But what do we know about the sum of the angles in a triangle? We covered this last lesson, I believe. And so we know that the sum of the sum of the angles in a triangle is 180 degrees, right? So we know that if this is 45 degrees, this is 90 degrees, and this is also 45 degrees, right? That makes sense to you guys, right? Because just so that the sum of the angles in a triangle are 180. So maybe we can try to find the area of this triangle. But as we see, what do we know about these types of triangles um, that have the same angle here and here? Well, remember what I said last class about the angles and the side lengths opposite to them, right? So if we know that if we say this is x, and if we say the side opposite to this 45 degrees is 12, right? Or uh, or not 12, but this is so this height is 12, right? So this height is 12. So if we say that this is also x, what can we say about x or what can we say about both x's? They're equal, right? I mean, I kind of gave that away, but So you can that's how you can relate the angles in a triangle to the sides opposite to them, as like um, yeah. So that's how you can relate angles and sides opposite to them, which is that if they're equal, then the sides are also equal. So this is x and this is x, right? And now similarly, we can focus on this triangle. Uh, so this triangle, this little triangle, right? Same thing. This must be 45 degrees as well, because if you're looking at this triangle, you have 90 degrees, you have 45 degrees. So you need another 45 degrees to make it 180. And so we know that again, this height is 8. Well, how about we try to calculate the area of this triangle, this big triangle, this medium triangle, right? And you'll see why I said medium and not small. So we know that this is 12, but we know that this is a 45, 45, 90 triangle. So we know that if this is 12, right? Um, so this must also be 45 degrees because this is the height. 12 is the height of the triangle, right? So this is also 45 degrees. This is also 45 degrees. And so we know that we can just calculate. Yeah, so if this is 45 degrees, this is also 45 degrees, then this side must also be 12. Does that make sense? And then similarly, this if this side is 45 degrees, and then this side is also 45 degrees, and the side opposite to this angle, which is uh let me which is this side right here, that must also be 12, right? And so we see that to compute the area of this big triangle, we see that uh the height is 12, and then the base is 12 plus 12, so 24. And so our area is 144 for this big triangle, right? And why did we add the 1/2? Because that's how you compute the area of a triangle. It's 1/2 base times height. And similarly with 8, we can do the same thing. So we'll get that the base is 16 and the height is 8. So the area is 1/2 times 8 times 16, which is going to give us 64, right? But now we can't just add these up and get to the answer, right? Because what are we missing? We are missing the height of this little triangle. Because you because when you because think about the parts and the whole concept and geometry, which is pretty important. So when I constructed these triangles, right? So this triangle and then this triangle, right? When I added the areas up, I added this common area twice, right? One while I was doing this computation, and one while I was doing this computation. But do we want to account for this area twice? No, right? We only want to account for this area once. So if we calculate the area 2 times and we only want to get once, what do? We just subtract one. So we just subtract the area 1 time, and because 2 times the area, and we want to get to 1 times the area, so we just subtract the area 1 time and get the area that we need, right? So what's the area of this? Well, we know that this is 45 degrees. This is 45 degrees. And so this must also be 45. So, well, yeah, so this must also be 45 degrees. And this must also be 45 degrees, right? And so we know that this is H, and this is opposite to a 45-degree angle. This side, which is also opposite to a 45-degree angle, must also be H. This is becoming a bit messy. Just gonna So this side must also be H because it's isosceles. And so similarly, this side must also be H. And so the height of the area of this triangle is 1/2 times H times 2H, which is going to give us H squared. And now we add everything up. 144 plus 64 minus H squared. Because remember, we when we did this computation, we calculated this area two times, right? So we calculated this area two times. We only want to calculate it once, so we just subtract this area once. And this, as the problem says, is 183 square feet, right? So we can add this up, which is 208 minus h squared equals 183. And so h squared is going to be 25, or h is going to be 5. So what is the value of h? The value of h is 5. And believe it or not, this, yeah, so Hubert, as you said, yep, that's right. So, believe it or not, this problem was actually, I believe, on problem number 24 or 25 from last year. And you guys saw that this problem didn't require anything fancy. It didn't require techniques that like we haven't seen before or covered before, right? This was done with the basic techniques that we covered in class. Some of the angles of a triangle, uh, calculating the area of a triangle, and everything, right? But all it needed was just for you to see that if we extended this length beyond this point here and made it touch here, and if we did that here as well, we would be looking at a triangle that had 45 as an angle and 90 as an angle. So we know that the other angle of this triangle must be 45 degrees. And similarly here. So we know that this is an isosceles triangle, and we already know that the other two triangles are isosceles as well. So we are able to find the area of these triangles and then subtract the area of the small triangle to get the actual area of this figure. And how did we get to this triangle making process? Well, the way I would think about it in the context is that, okay, if I look at this figure for the first time, I see that this doesn't look like um, a triangle to me. It kind of looks weird, but then again, it looks like an almost triangle to me, right? Because I'll just raise this figure so that we can see what I'm talking about. But if you look at this figure, if you look at this figure, right? Doesn't it look like two triangles to you, but two almost triangles to you? So if you had just one more thing, it would become a triangle. So all I did was just complete that statement. So if it's almost a triangle, why not just make it a triangle, right? So like that, and then just like the whole problem just goes from there. And so that's all you had to, and that's like the main key, I guess, point that you had to see in the contest to solve this problem, which was a problem number 24. So again, I'd say just try all the problems, and especially think about the different concepts that's needed to solve the problem, because oftentimes they're really not that fancy or something that you've never seen before. It's likely something you've seen before. And so with that, we'll conclude our lesson for today. Just look out for the video of our lesson, and we'll send homework problems. And yeah, I think that's it. Um, and we'll send out the meeting link and invite for the next lesson as well. Thank you guys. Good luck on the MCA as well.